Hello, good morning, everyone. This is Bharat. I'm starting the basic of thermodynamics of a first chapter. It is very much relevant to your GATE syllabus and the PK Nag book. In PK Nag book, first chapter, they will cover almost the basic of the thermodynamics, basic laws and basic equations, and on the basis of that we will cover that basic topic which will be which will help you in your gate preparation. It's only a basic thing which it might help you in remembering those formulas and the basics whichever is required. The thermodynamics is basically has the fourth law, and in which they will include zeroth law as well. Zero law is it says that if two body independently thermally equilibrium with the third body, then these two bodies are thermally equilibrium with each other. And this phenomenon basically used to calculate the temperature, because if you relate the temperature with the third body, then you can relate to which either. So on the basis of this law, we actually used to calculate the temperature. And if we goes to the second law of thermodynamics, first law, you can say zero, and second is first law. First law is like common law. It's the energy neither be created nor be destroyed. It just convert from one form to another form. It's as simple as that. And secondly, this is the another statement is that the total energy of this universe remains constant. And you are very familiar with this statement. And in this statement, you can simply says that every matter is whatever it is, that it is only in the form of energy, and it cannot create it, cannot be destroyed. Just like you take fossil fuel, you just yeah, it is in the chemical form, and after you if you put into the engine, it will get burned. And from that some amount of energy is uh, the total fuel is converted into the some ashes and some other form, and also in the form of heat. And from that heat, we are taking some part of that heat, and it will convert into the mechanical energy. That is nothing but you're converting one form of energy into another form. It's like a chemical energy into mechanical energy. And second statement, the total energy of universes remains constant. That is, you can relate with the entropy, and you can relate with the total mass of whatever we have in our universe. It will always stay in the universe. Similarly, the entropy of a system, whatever activity is taking place on Earth or in the universe, it will always increasing the entropy. Entropy is nothing but unwanted thing that is we are creating, and we are emitting into the universe. uh, Next we come to the second law of thermodynamics. Second law of thermodynamics is basically uh, says that how much quantity you can conserve. Whatever we said it's like you can convert one form in one form to another form, but in that we are saying that how much exactly, how much quantity we can you can anyway you can convert 100%, but it is not possible. Some amount of unwanted energy have to be released in that energy. You have two type of energy. One is uh, high grade energy and low grade energy. High grade energy always can be converted into 100% in the another form. It's like electrical energy. If you put 100 kilojoule of energy, kilowatt into the bulb, and it will create 100 kilowatt of heat. Similarly, if you take 100 kilowatt of heat, and it if you try to convert into the electricity, it the little amount of electricity you can able to generate from that, it is not as simple as that. And it has basically two statement for the second law of thermodynamics. And the first statement is related to the the Kelvin Planck statement, in which he says the limitation of uh, the machineries, and it says that it is impossible to construct a device which sole effect is to operate. It is impossible to one a minute. It is impossible to construct a device which sole effect is it will not work on a single reservoir, which is nothing but it cannot operate in a single reservoir, that it will extract the energy from that reservoir, also emit the energy in the same reservoir, and it will continuously running. It's like if you're if you taking petrol from your bike, and the emission pipe is also putting in your petrol tank, and it will goes on. It never happen. You cannot see in the universe this thing. And the another statement, Kelvin Planck statement. In this Celsius statement, the Celsius statement, Celsius statement, sorry, Celsius statement, in which it says that it is impossible to transfer the heat energy from low temperature to high temperature, because you can see in the universe as well. If you put the rod in the fire, it will transfer from the high energy to low energy. It is not possible. It has never happened that it is you are transmitting that heat from your body to that fire. It's never happened. And these are the laws of and the third law is talking about the entropy, and it is like the ultimate the energy you're wasting, and in which it says that the entropy of a system is zero at 0 Kelvin to the crystal structure. It's a proper definition. You can say at 0 Kelvin, the entropy of a crystalline structure is zero. That means everything is stopped, and no action is taking place, and nothing is going on. It's like completely dead state. If it is if you're not emitting energy, it's not you are dead. If you're dead, then you are not able to emit the entropy, that kind of situation. And if entropy is not creating, that means nothing is moving, everything is in stable position. If you moving towards the other thing, yeah, it's a B. What I have did, I have taken some random question in between. Whatever I have taken notes in which you can find the random thing coming in between. So it is just somewhere question, some like it's a IES question or ISRO question, some sort of question were coming together, and I have put into my that notebook. So might well I'll explain in between those as well, because I have take as a note. So in this, you can see in the top of this PDF that atmospheric pressure is always decreasing with respect to your altitude. You have seen that if you goes beyond a certain gravity of our Earth, you feel the vacuum. In the similar way, the density also changes with the altitude, because you can see that that pressure, whatever the water pressure is, that if you go into the depth of water, you will find you will feel the higher pressure, and the pressure create density. Pressure has a very minimum amount, a minimal effect on the density, but yes, it does affect. And in the air, it varies much, because the atmosphere at the down level, the density, the air density is quite high. And almost everyone knows that the isothermal process is like a temperature is constant, but in IES sometimes they use as a hyperbolic expansion, hyperbolic systems. Hyperbolic is nothing but the isothermal process. And the study which were taking place in the engineering, it has the engineering we do classical thermodynamics. We actually focus on that, and the statistical thermodynamics is basically focus on the research area. And as an engineer, we always focus on the application, not on the basis of on the research field. So it divides into two field. One is microscopic, in which the focus is totally based on the bunch of molecule. You can take like a bucket of water. If you study on the bucket of water, how does it behave when you start hitting from 0 degrees Celsius to 100 degrees Celsius? What is the effect? And that effect is not in a particular that water. I'm not going to in the depth of molecule. I'm just uh, analyzing that how that total bucket of water is behaving. That is microscopic. And microscopic is nothing but the whatever that bucket of, we are not think in this study, we are not thinking about the bucket of water. We take one atom of that water, and it's just like one drop of water, and we study that entire drop of water, that how this behavior. And from that we actually come to know that how this completely thing going on in that water. This study is related to the statistical, and in engineering field we never thought of that because we never go into that depth. So we actually focus on the only microscopic studies, and it's called as the classical thermodynamics, whatever you study. And second thing, if you want to create a work is basically a path process. You will get to know afterward that what is path process, what is this point function and path function. And if you create this minimum this boundary phenomenon. Boundary is nothing but whatever you know that bound something inside. And this boundary phenomena, boundary uh, type of boundaries. Sorry. Sorry for the disturbance. To this heat and work is a boundary phenomenon, which is nothing but it can recognize only when it is it crossed the boundary. It's like if a toothpaste is coming out of this the tube, then only we used to get brush. Otherwise, it is always there. And same thing. It's like heat and work. Heat and work is whenever you cross that boundary, then only it is useful. You can recognize it and you can measure it. Otherwise, it is impossible. And to get the work from some sort of system, it has to move that boundary. Otherwise, it is not possible to generate the work from that system. And in which there are two types of boundaries. One is adiabatic boundary, and second is diathermal boundary. Adiabatic boundary is nothing but you cannot transfer heat through it, which is like completely anti-heat. And its resistance is infinite. which is nothing but it has the infinite resistance to the heat. It will not allow to pass the heat through it. And the diathermal body is nothing but it can little bit pass the heat into throughout the body. And this is day to life, whatever you see in human body, anything, whatever come in across to you in this universe, it's everything is thermal. It has some sort of resistance, but it's not possible that you should it's not in the universe that you can if body is present which is not allowing the heat to through it. It might differ with the body to body, because it's you could, if you take a break, it has a less heat transfer. Then you can take metal, it has something, it transfer heat in the greater level, in the it varies with respect to their material properties, material to material. And if it goes to the system, thermodynamics has a almost three system which is very common systems, that the closed system, open system, and isolated system. It does use in a very in for in a gate question. People, they were mostly focus on these two sentences. The system is open and system is closed, and there is a flow system, and there is a flow system and unflow system. That you will come across these two words. In the closed system is like you have packed something in it and you focus on that. It's like if you focus on the gas cylinder, and the tap is closed, and you hitting it, and after that you and realize that what will happen. This kind of situation is the closed system. And in this closed system, if you take a gas cylinder, it's not inconvenient, but if you get it, heat up that gas cylinder, you will realize that you can heat it, but you cannot decrease that mass of whatever the content in that cylinder. You just only able to heat it, and after that if you stop the heating to that system, it will come to its original position, and that total whatever heat it has gained, it will relieve. But the total mass of that content is always remains, and that's why it's called as the control mass system. And second, if it goes to the second, is open system. Open system is like day life. It's uh, common things. We get something and we are emitting something, in which something is like air is also coming. In thermodynamics way, everything is coming and everything is out, going out. It's like a mass is never constant, and the energy is also not constant. If you take a compressor or a pump, water pump, if you think that the impeller is a system which is stator is, you can say, as a your system, and the amount of water and the energy that it's like a different kind of energy it has in it. It will come to the starting position of that impeller, and when it would deliver that water to the outer that delivery pipe. So that 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 energy, you are adding energy into that water as well. So the whatever that mass is also living the coming and living in the system. And secondly, the energy is coming, the energy which is included into that water, it is also coming and living through that system. So that system is, and it's common, you can see in the turbine, compressor, pump, etc. And isolated system is in the university you cannot find such a suitable example, because it never happened, and you cannot feel it. but only you can imagine. This is imaginary system. You always try to do that in the form of, you can say, people. Scientific people always try to do that, and the best product of that application is thermoflux. Thermoflux, you retain your heat energy. It's like if you wrap up your uh, roti in that aluminum paper, it will last a few more minutes heat, and that food, whenever you open after 2-3 hours, you will get same sort of it's like it feel like it's just cooked food. And similar thing, the thermoflux is there. If you put the food into it and some sort of water into it, it will it will it will it will store that heat. And you can say it not store, because after some time it relieves its heat, but it take time to relieve its heat. And hypothetically we used to call it as a isolated system. And in a big hypothetical way, you can say the universe is the best, because I don't know where is the universe end and where it start, but you can say this is universe uh, contained whole mass as well as whole energy, but no one knows whether where is the universe. And this is the best example. Thermodynamic people used to call as the best example for the isolation system is the universe. I don't know how much it is correct, or whether it doesn't has any proof that universe where it start and where it ends. It also has the homogeneous. It's a basic form of the these two, and it's been never asked in this gate, but it might ask in the IES. So it's a homogeneous system in which the uh, mass of the uniform throughout the volume. There's nothing but the if two this if you the system is there, and the mass, whatever the mass is there, the volume remains constant. And the heterogeneous system, it no, it doesn't. uh, if you come to the property of system, everything has its own property. And with that property we can able to define that thing, and we can check their values, which can check their quality. We can exactly we can exactly say this is whether it is good or not. So there are two, basically they are divided, whatever properties they are, it divided into two different things. It's like extensive property, intensive property. Extensive property is does not it's based on their mass, that how big it looks like, how small it is. On the basis of that, they used to divide this quantity. And another quantity is intensive property. Intensive property is not depend how big is that, how small is that, how does it looks. It doesn't depend on that. And in the in the in the form of in a thermodynamics way, those quantity which were depend on the mass is called extensive property. And those quantity who are not depend on the mass, it's called intensive property. And if you get the best example for the extensive property, if you get volume, 2 liter of milk, 10 liter of milk, it does varies. That volume varies. Mass is also vary. If you get like 2 kg of sugar, 5 kg of sugar, the mass varies. The quantity also varies. Entropy, enthalpy, uh, this is constant volume head, constant volume. This is somewhat varies, because entropy is also varies with the quantity. If you're burning 2 liter of fuel, the the quantity of the entropy generated is quite somewhat greater if you burn the 5 liter of fuel. Enthalpy is also in the same way. The enthalpy of water, if you take 2 liter of water, then if you heat it, then whatever enthalpy is required is somewhat less. And afterward, if you hit it up to the 10 liter of water, then you need a more enthalpy to create that. In the similar way, if you take the example of intensive properties, if you take in the form of kg or in the form of a droplet, if you take 1 liter of water, and it's come into the form extensive. But if you take one drop of the property, and that the drop of the property is similar to the 1 liter of water, it's like density of water. If you check the density of 100 liter of water, then also it is 1000 kg per meter square. And if you take a density of a single droplet, it is also in the it is also 1000 kg per meter cube. Similarly, specific volume, specific specific, that word is, if you take that specific quantity, it's nothing but uh, if you divide anything with respect to the mass, that uh, if one liter of water 1 liter of water per its mass, that 1 kg of water is the one, it required, if 1 kg of water you take and it heat it, and its weight is around 1 kg, then it is one kilojoule per kg. This is nothing but your whatever you, if you, it becomes specific afterward, that if you divide it with mass, and whenever you do the same activity on that, you will get the same result. If you um, if you boiled 1 liter of water, and it's yeah, afterward, if you take this another 1 liter of water, the same amount of heat you will require. This is become specific afterward. And every quantity become, whatever the quantity is in the extensive, it will become the intensive when you divide with the mass. It has and it is there is two the properties, like some in thermodynamics you can measure some quantity and you cannot measure some quantity. So in that you need to do a mathematics. It has some sort of way that to find out the relation between this measurable quantity. It's like a pressure, temperature, and volume. You cannot calculate the enthalpy. You cannot calculate the energy. You cannot calculate the entropy. You can you can calculate this pressure, temperature, or volume, and with from that calculation you able to calculate this uncalculated quantity, unmeasurable quantity. If you take the ratio of two intensive property, you will get extensive property. And if you take a ratio of the two extensive property, you will get the intensive property. And the best example is, if you this density formula for density is mass per unit volume. Mass is also extensive, volume is also extensive. The product is coming out of it, the density. Density is intensive property. Similarly for the extensive as well. And there are the properties which every quantity, pressure, temperature, volume, these are the property. And this is the point function. And you can say the property, uh, if system has their property, it's always in the point function. You can integrate it, and when it is the property of a system, uh, of a substance, it will you can take a cyclic integration of that, and you can take an exact differentiation of that. But if it is not the property of system, You cannot take a cyclic integration of that, and you cannot do a total integration on it. And there are also in the there are two form. It's a path function and the point function. Path function is nothing but the way you move ahead. It's like everything is depend on where you are moving and where you're going. Take an example. There are two city. One is the Mumbai, and second is the Bangalore. If you're moving from the Chennai, this Bangalore to Mumbai, you can take different routes. You can go by air. You can go by something else. Like there are many. If you join 2 point, if you ask someone ask you if you want to join, how many way you can join? It's like infinite way you can join two things. And uh, in that way, every whenever you check, go with a different path. This is nothing but path function, because every time you will not get the similar distance. Sometime you afterward you will continuously increasing your length of that path. And the point function is, it does not depend whether which path you're following. It's only talking about the 2 point, whether when you're at the Bangalore station and when you're at the Mumbai station, and how much it is, whatever route it is taking place, whatever route is taking, it doesn't count in that. It is only focus on the 2 point, not on the third path. In similar way, I will explain in the thermodynamics way afterward in coming lectures. Uh, just keep in mind this few things. It will be quite helpful to you. Heat is a path function, and work is also three things is there, which is path function in the thermodynamics. One is heat, second is work, and third is entropy, irreversible entropy that created by irreversible process. Reversible process entropy is also a property, and it is a point function. And this is pressure, temperature, enthalpy, entropy of reversible system, and energy. All these are the point function. It only depend on the 2 point end point. Does not care about what path you have taken in between, and what is going on in between. You don't care about this. You just only focus on that. This, it's like, say, you can take the example. The best example I have can give is uh, some company, one manager is there, sales manager is there. He has given some target to you. He don't care whether what method you apply to sell this product. He only needs the target. He only ask about the target. Similarly, this property are like that. It's only about the output, not about what you have done in between, what you said to the other people. They don't care. Only they need is you should fulfill your target, and you should reach to your target, and afterward just inform me. That's it. And this is like two things there. Whatever is path function, it's not a property of a system, and it is not exactly differentiable. And whoever the properties of the system, it is exactly differentiable. And it's a point function. After we move to the in depth of this chapter, in which it has the cycle, you come across that many cycles is going on around you. Cycle is nothing but when you go to the some point and come back with the same point. हाँ ये तो थोड़ा वेळा ना. So similarly, you can sorry for the disturbance. Yeah, we are on the cycle. Cycle is the in thermodynamic definition. Cycle is the process which come back to its original position without leaving any strain on the external or internal thing, like external thing. So it will accurately correct on that same point after completing its process without leaving any effect on anything, just like it never happened. And this this is all property is a state function, point function. I have just explained to you before. And this is the Gibbs function. Gibbs function is the Gibbs law, in which you can find out the degree of freedom of any substance. It's like a Pf plus C plus 2, and in which P is the phase of the this, F is the freedom, and C is the component in number of component in that thing. You will find afterward whenever it comes. The example of this is water at a triple point. You can say this concept it will be covered in the fluid dynamics, but in that position, the component will be always remains one. Phase is one. So the degree of freedom of that is 3. Single phase 3. 3 type of process. There are two process. One is the reversible process and another is the irreversible process. In which reversible process is never in this happen in this universe, because not a single process is reversible in this universe. The process which is not come to its initial state without uh, without it's like if in the thermodynamic definition, the process which returns original state without putting any strain on the external system, it's called as the process. And irreversible process is the process which never come back to its original state, or if it come back to its original state, still it uh, give external strain. It produce some sort of effect on the external or internal things. And irreversible process is everywhere. Whatever process you're seeing is, if I raise the hand, it's irreversible process. Cannot put the same hand below the same position. And this is yeah, there. If we try to achieve this reversible process, it's not possible to achieve it. But in hypothetical way, people used to think in that way, that process is reversible if it's very extremely slow. That if you want to travel 1 mm, like hundred of years, you need to work. 100 of year it will take to move 1 mm. That kind of slow process is required. And this is this mostly the isothermal process used to called as the reversible process. And it's a very slow process. And irreversible process, it's like whatever day-to-day life the process is happening, it all are the irreversible process. And yeah, this is very fast process. It's like rising hand. I don't take much time to rise it, and I cannot put into the original position. That is irreversibility. And this process, it's adiabatic process. There is uh, concepts called as the quasi-static process. Quasi-static process is the process nothing but the process which take infinite equilibrium state, moving from one state to another state. And in another way, it's like whatever reversible process is there, it always a quasi-static process, but vice versa, it has never been true. If it is quasi-static process, it may be or may not be the reversible process. And the type of equilibrium, if the process is going on there, it has to some sort of equilibrium need to be maintained. So the thermodynamic equilibrium, it has a three type of equilibrium. One is the thermal equilibrium. Thermal equilibrium is nothing but throughout the process your temperature remains constant. Sometimes you used to put as the temperature remains constant. So that is nothing but the thermal equilibrium. Mechanical equilibrium, we never just mostly focus that the force is uh, that force is developed, that whatever force pressure is applying on the system, it's nothing but mechanical. And this mechanical, the in a definition way, that throughout the process there will be no external forces apply on this system. It's called as the mechanical equilibrium. And chemical equilibrium is the equilibrium in which throughout the process the chemical composition of this system will remain constant. It never varies throughout in between that this process. That is equilibrium position, um, chemical equilibrium. And we always come across this ideal gas. It's never we cannot find the ideal gas in between because it's never occur. But for the simplicity of study, we need to assume something, and this assumption is the ideal gas. The ideal gas is nothing but the gas which in which the no intermolecular force of attraction and repulsion with taking place. And this is not in the real condition. In real condition you can find this all and this is the very common you can find everywhere. So we continue this session in the next part of this lecture of the first chapter. Thank you.